Okay.
All right, my name is Jonathan Dominguez. I am a civil engineering major.
Oh, my name is Ahmad
Oh,
already.
you're on mute. So we just start over again.
Okay.
And I just,
All right, start over.
all right,
Yeah.
okay. My name is Jonathan Dominguez, and I'm a civil engineering major.
My name is Ahmad already. I'm a computer engineering major.
My name is Amin Kadakia, and I'm also a computer engineering major.
Okay, and today we're going to be talking about the minimizing energy from residential HVAC use. And before we get started into how we got the code and how we have to be able to run it, we have to consider some various different challenges when it comes to HVAC use. And those challenges includes user behavior variability, which means like uh, there's going to be different conditions going to be set for the thermostat. So let's say uh, there's some buildings that would like it really cold, they like it really hot. Those really differentiate the energy use of the HVAC. And besides that, that also depends on the climate dependence, with systems behaving differently in various geographic locations and seasons, which different HVACs can be in climates that are particularly very hot or very cold. It all depends on how much energy that HVAC is really being put through to set those standards that you want. And also building specific factors such as insulation, size, and age. The older the building is, the more energy the HVAC is going to be using. The newer the building is, the more effective the HVAC is going to be. And then also we have to consider the sensor and data constraints, which makes real-time monitoring and optimization challenging. And then the value of the data model in this case, it has a tendency to rely on physical models based on complex parameters such as the building and material mix, and requiring expensive calibration time. And the data is really driven in models such as machine learning and statistical regression models. But on the other hand, we have to learn the patterns from historical data without requiring cumbersome and manual calibration. Now, this also enables real-time estimation and control, especially when combined with the sensors. And we have to improve precision and reduce sophistication, particularly when learned from abundant data sets. And I'll scroll down a little bit. Now, explain the analysis, the data analysis. This database commonly constrains with time series measurements for thermostats, smart meters, and sensors in residential buildings. So it all has very different uh, variables to look into. And common fields such as would be indoor temperature and outdoor temperature, and also the heating and cooling, whether if it's going to be on or off, which would be also be in the HVAC status, and energy consumption, which is basically the amount of electricity consumed. And then we're going to be reformatting some analysis, rename columns for readability. Now, there's also going to be, uh, it's going to vary once the code has been laid out. So, for example, the indoor temperature in Celsius, that's going to be in TN, or an outdoor temperature that's going to be in TOW, and so on and so forth. And then we're going to be explaining on how the code actually works to find out the HVAC consumption, energy consumption.
Okay, so for starters, for the regressor, I used a random forest regressor, which is an ensemble machine learning model made up of multiple decision trees. It works by averaging predictions from many trees to make a final estimate, which improves accuracy and reduces overfitting. Now, why is this a good choice? Random forests are good for regression problems like this because they can handle nonlinear relationships and are less sensitive to noise. Now, as you can see, the data it uses is 8 architectural features as input: relative compactness, surface area, wall area, roof area, overall height, orientation, glazing area, and glazing area distribution. Now, what does this model predict? Well, right below that, you can see it predicts two outputs: heating load and cooling load, which are energy efficiency metrics for a building. Now, in the performance evaluation, I split the data into training and testing sets and used two evaluation metrics to measure performance: R squared score and RMFE. Scroll down a little bit. Now, you can see that we have the R squared score, which is the coefficient of determination, This will tell us how well the model explains the variance in the target variable. An R squared close to 1.0 means the model predictions are very accurate. My heating model had an R squared of 0.998, which is excellent, and the cooling model had 0.971, which is also very good. Now, for the RMSE, or root mean squared error, it tells us how far off the predictions are from the actual values on average. A lower RMSE means better performance. For heating load, the RMSE was about 0.42, and for cooling load, about 1.66, both of which are low and show that the model is reliable.
Okay, so I did the user interface portion of the project. So first, um, what is a user interface? So the user interface is a simple terminal-based input system that allows users to enter values of the 8 architectural features. So as you can see, I inputted I made input prompts for relative compactness, surface area, wall area, roof area, overall height, orientation, glazing area, and then glazing area distribution. So I made it so anybody could really enter these values and get predictive measurements out of them. So I made sure to include ranges, like typical ranges for each of the following agricultural factors. So obviously you don't want somebody putting in 100 for relative compactness, because then that will make the regressor model like not work or not worked effectively. So obviously I put 0.5 to 1, 500, 900, 200, 450, and so on and so forth. These are all just general ranges I got from the CSV file from the data set. Moving on. These inputs are collected into a NumPy array, and they're converted into a data frame with the same feature names as the training data, and then passed into the training models. So you can see from here, I appended it to, and I turned it to a NumPy array, pass it through the models. And here's the feature names again. And then here's the, and then once the user enters the values, the models predict the heating and cooling load, and the results are printed with two decimal places. So here it is. I had already did it, but we're gonna go through it again and run the code again. There you go. And here's the R squared score, and also the the root mean squared error score. So it's 0.998, which is 99% accurate, and then for the cooling load, it's 0.97, which is 97% accurate. And so that's so on and so forth. So for relative compactness, we'll just input 0.6, 600. Let's do 350, 200. Let's do 3.5. Let's just do 4, 0.3, and 0. And here's the predicted heating load and cooling load. So quick recap, Jonathan did the literature part, and he also, helped us with individual odd jobs around, if he had issues with something, he would come and look at it. And Amon did the actual linear, not random forest regressor itself. So he loaded the files, dropped the extra column, and he renamed it, all that jazz. And then I did the interface. Some issues we had, especially one thing I can say confidently is that the extra optional part of making an interface to where you can add new values and it'll be generating new predictive data. After that, I really wanted to add that. I tried using the IPYNB widgets, and for some reason I could not get it to download. I could not get it to work. So I cut my losses and I just did it regularly. So yeah, I mean, that's it. Thank you for watching our video.